Hi everyone, I'm Dr. Vincenzo Romanello. I'm a PhD and I'm a nuclear engineer and nuclear researcher. I'm currently the president of Atomi per la Pace, which is an Italian pro-nuclear no-profit association. Today I'm going to present some slides about the perspectives of nuclear energy applications in the world energy mix. So let's come to the history of energy. The first milestone started when mankind started to exploit fire. The per capita energy rises to 1,100,000 calories per year. Then the second milestone happened when agriculture was discovered, and then per capita energy need rised again to 4,500,000 calories per year. Third milestone when metallurgy was discovered in 4000 before Christ. The fourth milestone was when water mill was mentioned by Antipater of Thessalonica in the 1st century before Christ. Fifth milestone when Arabs introduced the windmill technology around 650 after death. Sixth milestone in the 14th century in Europe when gunpowder was used as the first artificial form of energy, especially for war applications. Seventh milestone when in the 17th century when coal was introduced in industrial production, and then per capita energy need experienced a steep increase from 5 million to 15 million calories per year. Eighth milestone started when the crude oil use began to be used in the industry since the mid of the 19th century and the start of the Industrial Revolution. And this also was the start of the steep population growth, as I will show in a moment. The ninth milestone happened on December the 2nd in 1942 when Enrico Fermi started the first nuclear reaction chain in the history in the Chicago pile. The per capita energy need settled to 35 million calories per year. And the 10th milestone was still not reached, but it will probably take place when nuclear fusion will be a commercially available source. So what energy consumption means exactly? This is a map which shows the energy use in 2013 in terms of oil equivalents per capita. And here on the right up, we have the child mortality rate, and right down we have the life expectancy, average life expectancy. It is rather impressive from my point of view how these maps are very similar and can be overlapped somehow. So here we see the world population versus year, starting from year 1000, when mankind population was around 500 million inhabitants. And then we see a steep increase after the Industrial Revolution at the mid of the 19th century. And yes, in the beginning of the 19th century, we were around 1 billion. Today we're almost 8 billion. And there were some projections in 1970 what would be the population at the end of the present century with a constant growth rate of 2.1%. And you can see we would be 55 billions, but the reality is that there was a linear decreasing rate. Today, the growth rate today is almost half of that was in 1970. And in fact, the red line is much more realistic, and it shows that by the end of the century we'll be around 11 or 12 billion inhabitants. So it seems there isn't any population bomb despite the success of the book of Paul Ehrlich in 1968. A lot of energy will be needed, and many think and state that we have renewable energies, so there are no problems. In order to conveniently exploit an energy source, however, it should be continuous, divisible, concentrated, and redressable. In other words, if an energy source is discontinuous and dispersed, it could be still used, of course, but this would be paid with an increased technological complexity and cost. The key word for understanding this topic is power. As an example, if I get 100 watts per 1 hour, I will consume 100 watt hours, which means 0.1 kilowatt hour, and I will be able to light, for example, 10 lamps for 1 hour, so my whole flat. But if I get 1 watt for 100 hours, I will still have 0.1 kilowatt hour energy, but I will not be able to light any bulb, any light, anything. It is very difficult and expensive to store efficiently large amounts of electric energy. And the renewable energies, in particular sun and wind, are provided for free, in fact, by nature and are practically endless. But collecting and exploiting them is not easy nor cheap at all. The point is that even if I have a proper number of solar panels on my roof, for example, I want to run my TV, my fridge, or my oven, even if it is raining since 3 days or during night. And of course, there are no problems if the battery is the electric net. Somebody else takes care of the energy produced and pays for it. And it works until there are few users introducing variable power in the net. But it becomes definitely much more complex if every user starts to produce power randomly and introduces randomly in the net. The management of an electric net is not as easy as some people may think. Moreover, renewable energies, when not heavily subsidized, are rather expensive, especially when all the costs are properly taken into consideration. And according to some studies, like for example, Ferroni and Hopkirk in Energy Policy in 2016, solar panels are unable even to return the energy used for their fabrication. And we should keep in mind that in any case, a source of energy should be able to return at least 5 times the energy used for its fabrication, transport, management, and dismantlement. Renewable energies, in particular wind, were used extensively in the past, but when the world population was circa 1/10 of that which is today. What about nuclear fusion, which is the hope of many people? But let's make some discussion about this. Why nuclear fusion would be important? Well, the deuterium in 1 liter, the heavy isotope of hydrogen, so in almost 1/4 of a US gallon of ordinary water, can produce the same amount of energy of 300 liters, which means almost 80 US gallons of gasoline, or half a ton of coal. And technology could feed the humanity energy needs for the next centuries for sure. And it does not produce long-lived nuclear waste like fission. Here we have heavy hydrogen, so deuterium, radioactive hydrogen, so very heavy isotope hydrogen with 2 neutrons, tritium. They react, and the results are a nucleus of helium, which is not toxic, which is an inert gas, and the neutron. And what is interesting here is that we develop with this in this reaction 17.6 million electron volts. Electron volt is the unit of measure of energy. And it's interesting to remember that out of this 17.6 MeV, only 3.5 go to helium and remain in the plasma, and 14.1 MeV go to the neutron under the form of a very penetrating neutron radiation, which escapes from plasma, of course. So we have to remember that the energy of fusion is not developed in the form of heat as conventional sources, as even nuclear fission does, but like neutron radiation, which is extremely penetrating. It is necessary first to stop this radiation, transform radiation in heat, then transfer this heat to some water to warm up some water up to steam, run some turbine with this steam, and then electricity generator. This should be the process, and of course it's rather complex. But still, for comparison, two molecules of hydrogen with oxygen, which produce water, so which burn chemically, produce 4.88, so less than 5 electron volts. which means that nuclear fusion is 3.6 million times more efficient than conventional chemical reactions. But it's not that easy, however, to exploit it, because first of all, temperatures required for DT reaction, so deuterium-tritium reaction, are of the order of 100 million Kelvin degrees. And for comparison, the temperature of the center of the sun is only 15 million degrees. And of course, there are no materials which can withstand this kind of temperatures, so a couple of technologies are possible. One is based on magnetic confinement, which is ITER, the facility built in the south of France in Cadarache, and the inertial confinement in the National Ignition Facility in Lawrence-Livermore. Are two different approaches, however, respecting the so-called Lawson criterion. So in one, you try to confine the plasma at low density for a long time, which is the magnetic confinement. In the other one, you try to confine the plasma for a short time, but very high density. In any case, they are both rather complex and expensive technologies still to be developed and proven. And of course, also consistent amount of activated materials are produced as well due to intense neutronic field which is produced. Of course, if you add the neutron to a stable material, it becomes an isotope, often radioactive. Tritium does not exist in nature, and this is for a very simple reason. Tritium is radioactive and its half-life is around 12 years. So every 12 years, half of tritium decays. You cannot store it for a very long time and very efficiently. So it has to be produced artificially, and this happens by neutron capture in lithium. And we have to remember that it's radioactive substance, it's toxic, and it can easily contaminate water because it behaves chemically like hydrogen. So half of the energy, as tritium comes from lithium, actually comes from this metal. And lithium is an abundant metal on the Earth crust, but its price is already fast increasing due to battery applications, and we have to remember that on the contrary, on what happens with uranium, for example, lithium has also other applications, like for example in some drugs. Nobody really knows, by the way, what does it mean that mankind hungry for energy is burning water by nuclear transmutation, which means this water disappears forever. It's a very tiny amount of water. It's only the heavy water, which is 1 part every 6,000 parts. But still, it's nuclear transmutating forever. And the fusion technology, when it will become commercially mature, and it will take some decades more, will have to prove also to be economically convenient and competitive with other energy sources, and this will take still more time. In my opinion, it is unrealistic to expect to have fusion reactors able to provide electric power in the net at commercial prices before the end of the present century. So, then, what we should do, what we are supposed to do? We have an abundant, reliable, and economically convenient source of energy. It is nuclear fission. 1 kilogram of uranium oxide, which is the fuel used in current light water reactors, so volume of the size of a small apple with a 6 centimeter diameter, produces today in light water reactor, 50 megawatt a day, which means 50 million watts per 1 day, which means 1,200,000 kilowatt hour, which is enough to supply energy for 1 year to 200 houses and families, for example. And assuming a cost of $1,000 per kilogram on enriched uranium oxide, which can be even less, but let's take this number just for an example, it would imply a cost of fuel of the order of less than 1 cent per kilowatt hour. Of course, the price of nuclear energy does not depend on the price of uranium, which is only a tiny part. I calculated that, for example, that even if the price of uranium is multiplied by a factor of 3, the increase in the nuclear energy price would be only of the order of 16%. because the price of uranium was only a tiny part of the cost of the energy. The majority of the cost comes from the fabrication of the plant. However, today, a reasonable price for kilowatt hour, nuclear kilowatt hour, is of the order in the interval between 3 and 7 cents per kilowatt hour. This depends on many factors, which I cannot discuss here. And we have enough uranium to satisfy reliably the energy needs of the mankind for at least 1 century. But I will come back to this point in a moment, in the next slides. Nuclear waste can be safely stored in geological repositories, and in any case, reprocessing and transmutation technologies can enlighten further the issue. There is not enough information around for the public about transmutation, but there are companies which are running these technologies. A lot of scientists working on transmutation of nuclear waste. There are projects and designs of new reactors, of new machines. There should be something that should be explored more in detail. Therefore, from my point of view, nuclear fission should be considered at least as a bridge technology toward the fusion energy. In this picture, we see the pellet of a light water reactor or pressurized water reactor, which is used today on the left, and then the pellet of a fast reactor, and then a small sphere which represents the amount of high-level nuclear waste vitrified, which is produced by every citizen using only nuclear energy in 1 year. And for reference, there is one coin of €1. So the pellet, this single pellet, can produce the energy of 3 barrels of oil or 1 ton of coal or 17,000 cubic feet of natural gas. The pellet weighs only a little bit more than 7 grams. The small pellet on the right of a fast reactor can produce 3 times more energy than this. And okay, this is the glass, which I'm keeping into my hand, just to show a sample, to show how it looks like. It's a sort of volcanic glass, which safely encloses all the radioactive waste and isotopes, separating them from the environment stably. And there is the cask, which weighs almost half a metric ton, and which goes in the geological repositories. This is how it looks like. However, let's take a look about the materials balance today. We have a uranium mineral, and let's assume we have 10 metric tons of mineral. With the concentration of the order of 0.1%, we will extract 10 kilograms of uranium metal. Out of these 10 kilograms of uranium metal, we will obtain 1 kilogram of enriched uranium fuel, enriched up to 5%, for example, and 9 kilograms of depleted uranium, which has no practical use. Then we put this kilogram of enriched uranium fuel into the nuclear power plant, and we get, out of 1 kilogram, 950 grams of waste uranium, once again, and only 50 grams of reacted uranium, and which means plutonium, fission products, and minor actinides. Minor actinides are the isotopes heavier than uranium and plutonium, which are formed during nuclear reactions when the neutrons are captured by uranium and plutonium. So this means that only fission products represent the uranium which reacted and produced nuclear energy, which is only 3 or 4%, so 30 or 40 grams out of 1 kilogram of fuel, which means out of 10 kilograms of uranium metal. Plutonium and minor actinides clearly did not produce any energy. So this means that we exploit only 0.5% of the uranium that was extracted from the mine. Can we do better than this? Of course, we can do much better than this. Technologies exist. Let's take a look. So, still, we have the same scheme as before, but this time let's split the fission products from one side, which is the ashes practically, which has no use, and from the other part, the isotopes which are heavier than uranium, so plutonium and minor actinides, Well, if instead of using light water reactors, you use fast reactors, you can exploit the 9 kilograms of depleted uranium, even the waste uranium and plutonium, in the blankets of plutonium directly for production of energy, and the uranium you can be put around the reactor to be transformed in plutonium as well. This means that if you use the whole amount of plutonium, and not only 50 grams out of 10 kilograms, the efficiency is multiplied by a factor of 200. This is why Generation 4 reactors, fast reactors, could be the key of the problem. There is a prejudice toward plutonium and thorium, however, which can be trouble for this. First of all, let's say that plutonium is handled by some countries like waste, but it's not a waste, actually. We have to start properly about plutonium. Plutonium is a fuel. Virtually all uranium-238, which is more than 19% of the natural metal, which is extracted from mines, can be transmuted into plutonium and exploited for energy, as I showed in the previous slide, instead of being considered a waste. Plutonium drives the radiotoxicity level of the spent fuel also in the repository, and so separating and transmuting it could be even potentially convenient also from the environmental point of view. The plutonium reprocessing does not encourage, by the way, automatically nuclear proliferation, as some rumors say, because for nuclear bombs applications, you need clean plutonium, so poor in isotope 240, which is high self-fissioning isotope emitting neutrons, which is certainly not produced in power reactors. For obtaining the proper plutonium for bombs, you need dedicated reactors, or at least reactors which are refueled online, like Canadian CANDUs. By the way, also thorium is non-fissile, but is fertile, and it is 3 times more abundant on Earth's crust than uranium. And plutonium can be used to fertilize it, transmuting it in uranium-232. Let's come to the energy demand. What will be the energy demand? According to IASA and EPCC and many other institutes which study the energy consumption projections for the future, we developed in a study almost 10 years old this energy envelope. This is only nuclear energy request, and it is hypothesized that nuclear energy will represent only 20% of the share. And we see that by the end of the present century, the request of nuclear energy will improve by a factor of 8, roughly, with a steep increase starting from the half of the present century. But if we split this request, we see that this energy request will be mainly concentrated in Asia and in sub-Saharan Africa, of course, in developing countries, as OECD countries are already more or less developed, so the energy request increase will be limited somehow. What about resources? There are various types of resources, but what we agreed in a study that was published also by the Nuclear Energy Agency some years ago, the total amount of uranium, neglecting uranium in the seawater, of course, so simply using mine resources, is of the order of 40 million tons. But we should also take a look where these mines are concentrated, and they are mainly in the EPCC 2, so in OECD area. Developing countries have no big resources of uranium, and this is why fast reactor technologies and breeding technologies become extremely important from this point of view. Somebody says that with the present rate of uranium consumption, we have enough resources for 615 years. This is not how it works, and this is immediately clear if we think a moment to the energy demand that I showed before. So this is the natural uranium availability if we use conventional technologies, so light water reactor technologies, as I showed before, we would run out resources maximum by the half of the next century. Or if we take a look to committed uranium, even by the end of the present century. And we will have to go to unconventional resources, so in phosphates, non-ferrous ores, carbonatite, black schist, by the half of the present century, because we exploit at present uranium in a way which is not efficient at all. And these are, for example, the number of big mines, equivalent big mines that would be needed to fulfill the request. We have 10 equivalent mines today in 2000, and should become 80 by the end of the century, which is not a trivial task, of course. So, what does it mean? If the entire humanity use only the present technologies of light water reactors with a very inefficient exploitation of resources, we will consume the whole uranium mines by the half of the next century. And by the end of this century, we'll have to go to unconventional resources, increasing the price. Even this will not be dramatic, as I showed before. If only developing countries use light water reactors and the others use fast reactor breeding technologies, well, we will have an intermediate situation. If breeding technologies, fast reactors, are developed fast, then we will not even probably need unconventional resources. So this means that the generation 4 and the breeding and the smart exploitation of the resources is the key for the future. But of course, this doesn't mean simply the development of reactors, but even of the whole fuel reactor chain, which means fabrication plants, transport, processing, etc. So let's come to conclusions. The world requires a huge amount, and will require, especially in the next future, a huge amount of energy, especially starting from the half of the present century. We can confront this issue in only two possible ways. The first is reducing the energy demand, which means mainly depopulating this planet, which is the Malthusian approach, probably, or, as I prefer, providing the required energy to those who are rightly claiming their piece of cake. If we assume that mankind represents a resource for this planet, let's think, for example, that the higher the number of workers, scientists, researchers looking for new energy sources, treatment of rare and mortal diseases, and so on, if we consider mankind as a resource and not a bad virus infecting it, the second route is mandatory, in my opinion. But this requires, however, immediate and strong action of the civil society in order to push decision makers in the direction of our infrastructure construction and development. But in many places of the world, it seems to me that it is happening exactly the opposite, I have to say. In any case, it should be recognized that the biggest energy resources are not in the mines. The biggest resource is mankind and its capability to find new scientific discoveries and invent and develop new technologies, provided a rational, peaceful, and cooperative approach is pursued.